In this video, we are going to look at some really interesting examples of fractal art and see where we can find geometric series present in these visuals. So what I'd like to look at first is an example of a repetitive pattern. That's what a fractal is, where I have the first few stages of the pattern shown below. We start with a square. Let's imagine a unit square. And on the inside of that square, we place a circle of maximal radius to be contained within the square. When we move from one stage to the next, we insert a square of maximal size inside the circle from the previous stage, and then repeat this process of placing a circle of maximal radius inside the square. We then repeat that process moving from this stage to the next, and in the next stages that we don't have pictured here, we would keep inscribing these squares with circles within them, and then shading the difference in area. And the question we're going to be concerned with today is, if we are to continue this pattern forever and ever, what would be the total gray area shaded in the infinite picture? Now, the process we're going to use to solve this problem is going to be to take a look at the picture and very slowly and methodically find the measurements we would need to figure out the new gray area at a given stage. So we're going to start with the first stage, stage 0, where everything is as easy as it can possibly be. Remember, we're assuming that the square is a unit square, so it has a side length of 1, and we can determine the area of the square by squaring the side length, and it happens to be the case that 1 squared is 1, so we get a value of 1 right here. Next, we're going to determine first the radius of the circle, which in this instance is 1/2, half the side length of the square. We're going to use our formula for the area of a circle as pi times the radius squared in order to figure out that the area of this particular circle is pi over 4. Lastly, we'll determine the gray area that's added in this particular stage to be the difference of the area of the square and the area of the circle. In this example, 1 minus pi over 4. Now, the process that we're going to use when we move from stage 0 to stage 1 is going to be exactly the same. We're going to need to know all of the same information: the side length of the square, the radius of the circle, and the area of the two shapes that we have added on right here. Once we have all of those variables, we'll very easily be able to determine this new gray area that's been added in this stage. But the really big question is, how do we get started? How do we determine the side length of this new square from the information that we have? Now, I very much like this problem because the trick to making it work is to add to this picture a triangle. And the triangle that I want to add to this picture is shown in the visual above, where we have these two side lengths of the triangle being a radius of the previous circle. So in this example, the length of this side of the triangle and the length of this side of the triangle is 1/2. We can use our good old-fashioned Pythagorean theorem to take the side length squared plus the side length squared, and that will give us this length of the hypotenuse squared. And doing a little bit of algebra tells us that the side length of this square in stage 1 is then 1 over the square root of 2. Once we have the side length of that square, things get a whole lot easier. For example, the radius of the circle is going to be 1/2 the side length of the square. That distance from here to here is half of that total distance, so that's pretty straightforward. And then we determine the area of our new square and the area of our new circle by using just basic formulas for area: side length squared and pi r squared for that radius right here. And the gray area, again, just the gray area that we've added at this stage, is given via this subtraction of the area of the circle from the area of the square. Now, moving from stage 1 to stage 2 is going to work just the same as moving from stage 0 to stage 1. And in general, if we're at any given stage, the way that we're going to move over to the next column of values is going to be precisely the same in adding in this triangle. And all of this work we're going to do right away is just going to be to get us the value that goes right here. Once we have the value for the side length of the square, the rest of this column will fill in a very straightforward manner. So the way that this will work in general is we're going to draw in this triangle that we have shown in green right here. And a side length of this triangle is going to be given by the radius of the previous circle. And this distance right here, you can see, represents the radius of the previous circle. Just as we did with concrete numbers going from stage 0 to stage 1, I'll now do with variables. Whatever these side lengths are, the previous radius, we're going to take them and square them and add them together so that the length of the new square will be found from a Pythagorean theorem, a little bit of algebra, and what we find is that the side length of the square in the next stage can be found by taking the radius from the previous stage and multiplying it by the square root of 2. When we apply that in this example to get to the second column from the first column, we look over here to the radius of the previous circle, 1 divided by 2 root 2. We multiply that by root 2, so the root 2's cancel, and what we ultimately fill in right here is 1/2. Once we have a value of 1/2 for this new side length, the radius in this column will be exactly half of the side length of the new square. We can then plug in those values to general area formulas to find the area of the square, the area of the circle, and the total area added at this stage by subtracting those two things.